Next, we'll go through some of the things I think about every day for automotive, particularly the advanced ADS. It's pretty much, as I said before, integration that takes place so that we have more performance and less space. A lot of times it's the system integration of package level that makes the difference. You're going to see a lot more differentiation in memory too. Memory, traditional, most cell phones have flash memory in it, plus a little additional amount which is called dynamic random access memory. The same thing is true for automotive, particularly when you're storing a lot of dynamic data. Some of it will take place on hard disk drives or solid state drives. Solid state drives are made out of flash memory. But flash memory has taken a little bit of a difference here too. So early adopters of putting chips on top of chips were the memory companies. They were also the CMOS imager companies that built small cell phone cameras and such. But there will be alternative memory. Some are magnetic, some are resistive, and some are phase change. These are higher speed memories. You can get a lot more density in them. So as it comes to be with more advanced driving solutions, the memory will change as well. And then really the balancing between high performance and reliability over lifetime, system cost reduction, new players with new responsibilities, obviously through 26.2, and then the challenges of failure analysis. Because as we push things together, we make them less amenable to cross-sectioning, to do fault isolation and such. But there are new methods being discovered every day and tried out. One of the things that I showed you was the glass core technology, actually keeping glass in the middle. It's superior dielectric and very low insertion loss, particularly compared to both circuit board material and to silicon. So really the market there is for communication chipsets. On that particular device, there was 3 chips. One of them is a microcontroller, 32-bit microcontroller. Next is a codec chip for communicating a video. And then finally a Bluetooth low energy chip. All this within the size of your pinky fingernail. So there's great hopes for that too. As I said, you could probably hermetically seal this. We've proven it. You get excellent hermeticity. And as a result, you can trust your MEMS and sensors to go in there for packaging. You can put active elements on glass. While you have the glass exposed, you can etch in and metallize coils, antennas, and other solutions as well. And then glass can be pretty much either chemically etched or optically etched with lasers. I'm excited because we're getting a laser in-house, a femtosecond laser will actually drill holes in glass, fuse silica, and sapphire. Sapphire, you have to etch, chemically etch, but you can actually scribe it, and now the chemical etch will take care of the rest. And here's an existence of another concept by NE Silicon, basically an RF package, with the radio chip and the broadband chip in close proximity with the passives around that. As we're going through this, we have segments which are high temperature electronics. Therefore, we're dealing with materials that can handle the high temperature. We're dealing with high power electronics, MEMS and sensor electronics, and then finally communication. I won't read through every one of those, but this is the hopes, particularly from Dr. Raul Tamala at Georgia Tech, that is really focused towards this. If I can put in a plug there, they will have a symposium, a 2-day symposium called Future Car. It's on the Georgia Tech website. So there's another reference for being exposed to more of the infrastructure. And our glass core technology, or GCT, is based on glass interposers, where we treat it like a circuit board material. Structured glass substrates. That glass can, again, be fused silica. It can be sapphire as well for biosensors. It can be a hermetic glass package. You can imagine that an image sensor that has small pixels on that will probably need to keep both low particle contamination and also high hermeticity or low moisture content. Glass is very smooth, extremely smooth. You don't have to polish it as much or at all in using for MEMS and sensors. Then finally, glass is transparent, so you can actually deal with both optics and photonics. This is not glass-based, but a system in a package. We have approximately 3 chips underneath this plastic housing, but this is our Firefly product. This is an individual package, and this is the package with the fibers coming in it for high-speed data. So this is 14G and 28G, whether it be just transmit, just receive, or both in a duplex mode. But it gives you an idea that system in a package helps to reduce what's called an optical engine. You put it in the middle of the board close to a source like an FPGA, and it transmits at very high speeds. But this gives you a feel for what we have in-house too. So underneath that aluminum heatsink is that particular package. And future generations will then transition to glass. We use glass both actively and passively in those systems. As we look at, as an example, automotive lighting, there's newer technologies such as GaN, which is gallium nitride on silicon. Very nice for LEDs, the same thing for lasers and OLEDs, and then these digital micromirrors, which are usually in the projector displays. They've come from basically a simple consumer applications to something more sophisticated, such as the automotive industry, and all have roles within the automotive lighting. Some of the challenges were thermal management. Obviously, some of these are very high power, and as a result, need to be cooled in an effective way. If you do not cool them efficiently, there's problems with their, what is called internal quantum efficiency, where now the light starts to dim and could actually go dark. System packaging and device packaging, all of these have been through many iterations of device packaging. And then the system, more recently putting lasers into the high beams really have brought about some big changes in the system packaging. Qualification, again, just to cover the environment, particularly in the front of the car. So real briefly, these are the fan-out technologies that exist today. Originally, if we were to deal with a package on package, so there is a laser here. So what we have is the mobile application processor on the bottom and 2 memory chips on the top, basically providing a system solution. If the top or the bottom package were to be made in a wafer level package, first of all, the height would drop and the speeds could actually improve because of that. So we're going from a 1 millimeter to a less than 0.8, usually 0.75 or 0.6 millimeters tall. And again, in mobile products, it's very important to keep the Z height under control. So there are various ways of doing the fan-out FO type of packaging. And I won't go into those in detail, but many of the large semiconductor manufacturer or packaging houses are doing this under various licensing. So these are the suppliers in a little bit more detail. All of them are much, much bigger than my company, so we've got our aim high solutions in place, though we don't want to play at those million plus parts per day or parts per week numbers. But these people are very astute in the fan-out wafer level packaging. And as a result, some of those fan-out wafer level are in the radar world, and that therefore become quite easily. So you can make basically several hundred of these on a single wafer. And the beauty is all the packaging's done at the wafer level. And all you have to do is cut them out of a wafer. And the same thing is true with the Freescale 77 gigahertz system. Really inventive solution and can take up minimal space within the final system. So system costs, particularly since Infineon had started out with a lot of the IP here, they started out with the Atlas type chip, and again at 77 gigahertz, and then migrating today into much more larger platform. In this case, it was based into a traditional package, went into a mid-range where it now had what's called embedded wafer level bonding, so EWLB, and then going further into a 2-chip set, and then finally into long-range and mid-range types of radar applications. So this is where it will continue to diversify and be very innovative too. So the reason why I put red squares here is it usually takes this to do innovation within electronics. First of all, the technology and the device. Secondly, the package and how innovative it comes and more serving to the industry. And then finally, through a system architecture mindset change. So high bandwidth wireless, it's a changing landscape. That's true for most of the packaging and electronics, and is really geared towards next generation and self-driving cars. It's going to bring a lot more of this decentralized and centralized computing, and then the 5G-like communications, which I think will be very unique in its application for automotive. This is a blank slide of my error, but I want to introduce a few more levels of package integration. One of those is traditional things where we think of putting 2 chips on a substrate, system in a package, but it's a 2D system in package. We tend to do them as flip chip, so the active area is along the pink line at each site, and then we turn them upside down and then reflow the solder. We then take this substrate and reflow it on the system board. There are derivatives of this. One of those is 2.5D. And again, you take individual chips, you put them on either silicon or glass or organic material, and then you flip chip that down to a substrate, and then you flip that down to the system board. A lot more chip technology is starting to stack on top of each other, so you have basically a wire bonded chip on top and a flip chip there, and then the substrate. Now we can go even further. We can do a true 3D, and again, with doing 3D, you need some thermal solutions. You also need failure analysis and qualification process uniquely different. Or we can talk about complex 3D where we've got multiple things, such as a processor, memory, maybe a MEMS chip or a sensor chip, and an additional chip for support. Now it becomes a lot more complex. And then finally in the corner is the underdog, which I think in this instance never took off for the most part. And that's trying to have a vertical interconnect system along the edge. It's usually very unreliable, and as a result, a company with that acronym actually went bankrupt a few years ago. All right, this is a slide from Infineon, really just showing the hierarchy of different package types. And as trends went on, the speeds weren't sufficient. And eventually, when you're in the 300 megahertz, you're only in a ball grid array package. So speed is a very important part. And what dictates that speed is the package around it too, or at least that has a large effect. But the trending is to go to more of a high pin count. The pins are 80, 100, 144, 176, 292, all the way up to 516. So the I/O is increasing. You're also looking at microprocessors within the system, or MCUs. As we see this increase, we're getting from one package type technology, low speed, it's called thin, small outline package, QFN, quad flat, no lead, and so on. As you're going to the right, you tend to have a lot more I/O capability, and that's where the current MCUs are at, going and pushing towards that flip chip solution. Sensor fusion. I realized that last session you actually had a talk about fusion, but it's kind of unique. Here is one system where they take multiple sensors, both camera and radar, onto a single module. And again, I won't read through it, but really this has been defined, first of all, with cell phones.
and now has really come to be also in automotive electronics. Definitely there's a lot of distributed systems and system on chip within these vehicles. It's nice to have one module package. It's then generating a massive amount of sensor data. You have strong requirements to handle all that data as input. It needs to be consolidated, and finally it needs to be into an embedded processor. A little bit more about this. I'll switch over and I'll get back to sensor fusion and some of the things that could actually be game changers as well. Increased number of not designed for automotive. Everybody wants to be in automotive, but they have to really have some skin in the game as well. Zero defect quality and a 15-year plus year reliability. Basically, we have some choices here. We can basically modify the vehicle, which has high doubt that we'll do that. We can change the device mission profile. We can also do system level solutions, though they're not quite as enough, mainly through redundancy, external component protection, and cooling. So we're getting the reliability where it needs to be. And here's a small graphic on some of that. I'll expand on the chart a little bit more. And again, we have to comply with certain specifications and standards. There better be in place a quality management system, and then finally we work along with the Q100 standard that's in place for the basically the failure mechanism-based stress testing. This is a chart that's normally seen. Well, we have a few spots where we can have a big impact, particularly in test assembly and test robustness. So we actually go into test groups. I'll show you some of the tests that we perform. And then certainly at the end of it all, we have to qualify both the test group A, B, and G. But early on, we have to work with the people that are making the chips themselves and not just the packaging. So these foundry process reliability models are enhanced as we go forward to meet the automotive standards. On the left-hand or right-hand side, there's characterization, also statistical analysis. It's very important that all of our engineers, whether packaging engineers, assembly, process engineers, they all understand statistics very well. That's a valuable asset as we move forward. I won't go through each one of the groups, but certainly some of the tests underlying are very key to us doing the packaging design. And high temperature operating life, and particularly temp cycling and autoclave are kind of key for both thermomechanical stresses and moisture-driven stresses. Let's get through this. All right, so automotive, one of these things is not like the other. Automotive, definitely a lot more robustness in test compared to the commercial or industrial column there, with both stress testing, electrostatic discharge and charge dissipation model, physical and stress testing, unique stress testing, and composition of the tests themselves. So we're actually working towards a more robust automotive qualification schedule. Again, this comes from Freescale, but these are bathtub curves. We want to minimize all the entry here for safe launch. You can see this would be a conventional consumer product. This would be automotive to help ensure a 15+ type lifetime. So we have basically things that we implement, safe launch, and 8D corrective actions all throughout the process. So we can have many learning cycles to help minimize the amount of defectivity on the vertical axis. And the key thing here is that right slope is usually frozen after the technology, packaging, and product development have been successfully done. Things are getting hotter. We've realized that our enemy has always been temperature after the electrical has been solved, and a large portion of that is We started out understanding dynamic power pretty well, power dissipation, but there's also leakage taking place here. So when we want to successfully launch a product, we have to think about its thermal environment. Have we taken care of it? Has the thermal path been optimized so that we can really perform well? And again, temperature operations through automotive are described here for various grades. And again, I'll leave that for further reading. And power devices, we're seeing a lot more. As far as planar electronics, sintering have made a big difference. That glass pretty much has copper fill in there where we're sintering that copper into place so that we get a nice airtight, very low resistance and high reliability substrate at the end of it all. Sintering has made a big difference there. As I pointed out, the packaging can make a difference, the materials make a difference, and for power electronics, again, silicon carbide and GaN have made a huge difference, particularly since they're wideband and you get more power out of them. Cooling technologies still has ways to go yet because as those devices run faster, they run hotter too. System integration, whether we do it at the package level or at the system level, these are the things to consider. We need ultra-low inductance as well. And then the challenges, again, design to cost, power to weight ratio, power density, design for reliability or into reliability, and then system efficiencies. And then again, some of the failure mechanisms. Not too many semiconductor suppliers actually go the full range from -40 to 125. It makes it a difficult thing, but that's important for getting the devices to work for 15 years plus. Electric cars require high power, resulting in a high temperature electronics. So the thing that I've been advocating in my former employer, when you put 9 chips together all on the same footprint, you got to get the heat out, otherwise the devices will start to misfunction. There are creative solutions, whether it be applying heat sinks directly to the high-powered regions of the chip or chips. Materials will make a big difference, and then also putting active cooling in there. So vapor chambers are a big issue and solution. Vapor chambers are used now within data centers as a way to pull off heat more efficiently than just heat sinks. So that's been another implementation that's taking large scale. The data center said they'd never use water. I think within 2 years they'll use water to cool down parts. They're just generating too much heat to take it away through either heat sinks or vapor chambers. Dielectrics and other materials. Again, materials recurs again quite often in the solutions for any one of the technologies. And then higher rel, ultra high rel is important for meeting a under the hood type 250 for 8,000 hours. These are the typical tests that we go through. Again, I apologize for the font. It's barely readable. And, but environmental, mechanical, ESD, and electrical are kind of key here. SIP reliability, really looking at, these are very complex chips and modules and packages, and they have to really comply with the Q100. Complex, we usually work our way through the assembly process doing FMEAs, the failure modes effects analysis, really to help drive new materials, the multiple sources of silicon, and the thermal management. Most of those can be worked out through FMEA studies. And then finally, getting those solutions, a lot of times we do fault grading and also performance interactions when we do characterization. All right, now looking at some of the variety that we have here as far as systems that will continue to be enhanced, and then next generation for long range detection radar. This is silicon germanium type technology, high speed, very quick switching. We'll also be doing a lot more with package integration to help meet the cost requirements in particular. Miniaturization, Again, you can't afford to have LiDAR stay too big. You'll want to make it a little bit more integrated and with a smaller form factor. This is where I believe 3D photonics will make a big difference in it too. And I hope that glass can be a part of that. And then finally, when we go through these iterations on radar, we start bringing in both 3D mono and stereo cameras to enhance. A little bit more, a little flip back to sensor fusion. This is what's called a periodic table for sensors, or MEMS in particular. And you all remember chemistry, right? Okay. My wife's a chemistry teacher, so I can get away with this. But there are families of sensors. In some cases, they're one-dimensional, two-dimensional, three-dimensional for angles. Another one is for, granularity. This was really designed for cell phones in that they had quite a few sensors. Today's cell phones usually have around 10 to 14 sensors or MEMS devices in there. Now when you look at this, and maybe you're taking step data, or in case you're taking car vehicle distance, you can now integrate that into various things such as speed. You can take the angle at which the car is traveling in. If it's in a collision, you now know that with some electronic stability control, if it's starting to roll to the left side, you can start to deploy airbags soon enough. Now with this type of data and more sensors, you can actually do some very sophisticated things as far as now deploying maybe a call to emergency services. So there's combinations in here, and when you start putting them together, such as when we talk about compounds, we have more than one element. Now you can take your angular data and data frequency, and now you can sense different things to be employed. And that's where the chemistry of most of our ECUs and eventually some DCUs for both just a generalized sensor set, and now start to mix them. You can come up with different functionalities that are really taking full advantage of all sensor sets. And I really refer you to this type of site for the type of philosophy. Movia is a company out of France. It's basically an IP company, but they talk about the chemistry of motion, and originally intended for mobile products. So we have quite a bit of ECUs here within this system, but as you know, there's a domain controller too that will eventually evolve. This is from DSpace, and talking about the importance of knowing what the system is doing and being able to fuse the data that's coming back. And again, sense, understand, and act. In the case of MEMS, it's sensing something, looking up what that algorithm actually means, and then actuating something, whether it be brakes, airbag sensors, but it can come in these forms. Do nothing, because it really wasn't an important thing, and it knew that through the sensor fusion and took some action. It can warn, assist, control, and control in various ways. You've seen all of these plots. There's lobes going forward, backward, sideways. And so a lot of automotive companies are really giving careful thought, and electronics companies too, to try to make the best decision, whether you're looking forward, backwards, or sideways. And again, the classic description of a Google car. In this case, the various sensors are actually called out in the gold color there, whether it be 360-degree laser, LiDAR, radar sensors, position estimators, and 3D radar sensors as well. So it's strategically positioning them within the vehicle to basically sense as much as possible. On the smaller descriptors, it talks about the other set of sensors that are within the vehicle and technologies. There's definitely going to be more development work on sensors, really to create that 3D picture versus a 2D slice in time. That means more data. But as you can see, we've got quite a few technologies already in play in most vehicles, and looking for that impact on both cost, miniaturization, weight, and other things that become very important parameters. So here's a quote basically from the Infineon CEO, just really saying that the fatalities need to drop, but certainly we want less accidents, lower insurance, lower congestion, basically increased commuter productivity. I was actually interviewing for a job at Apple. They would send a van to my house. The van would be already Wi-Fi connected, so I'd be able to start my day as I walked on and not be distracted by traffic and fuel efficiency. Certainly safeties are through both sensors and processing information and computing. There'll be a lot of data involved, and fan-out wafer level packaging would be an important part of that. And they've really been showing that they can make radar modules using the fan-out wafer level packaging. They own the IP for a certain type of wafer level packaging. LiDAR, as you know, light detection and ranging. Some of the key things are it has both an emitter, a mirror, and a receiver. The emitter sends out the laser. After bouncing off an object, the laser returns by the mirror and bounces onto the receiver, and that's basically how it'll start to do mapping. There are some really cool things happening in the industry that most people don't know about, but there's a lot of innovation involved to try to reduce the size, cost, and provide more of a complete picture using LiDAR. And again, you're probably very familiar with the LiDAR suppliers that are in existence today. Again, some more principle there. I'll skip this. Some packaging, really, it has to allow for a definite size and reflectivity. There's a wavelength associated with that. The 1550 is now being used as a standard for silicon photonics to help with this type of light detection and ranging. And the package has to be small with an integrated driver. Much like that small Firefly product that we sell, it'll have to be ever shrinking to that point, because there may actually have a need for array technology to gather a much more complete 3D picture. They are running pretty hot at 75 watts. That's kind of a creative solution. A lot wants to force that out through natural air convection, but you can't always get that in Phoenix. And then a very high-speed device or short pulse. Some of the things that are actually incorporated are these photodiodes. A lot of them are called APDs, or Avalanche Photodiodes. These are the types of things that are involved in choices that you have to make. Some of them are very fast, but they're also very hot. Some are a little bit more efficient. High signal to noise ratio for the APDs. They're usually, when we have customers coming in to say, build us a component in the LiDAR system that'll be of this variety. And then silicon or single photo multipliers are now starting to change a little bit too. You get pretty good gain at a lower operating voltage. So a lot of good things in electrical for the system. This is the typical map that comes off from a LiDAR. This is the Valadyne system. And as you can see, the components in one of the displays are actually geared towards miniaturization and trying to make this stack smaller. And again, the principles behind it, there is some new work on really an integrated 3D camera, trying to bring in a lot of pixels. And this is that frequency modulated continuous wave LiDAR. Most of the work comes out of UC Berkeley. An amazing device. It almost looks like a camera itself than a LiDAR system. And I think, again, we'll see a lot more in this MEMS, electronic, photonic, all this built onto one single platform. So we have
what were viewed as fibers.
And then now we'll put them on chip material instead of fiber. All right, radar usually likes to operate in this range of 24 to 77 gigahertz. It's less affected by weather as opposed to a LiDAR system, and the data streams contain distance, speed, and object recognition, hopefully in the future, with lookup tables for objects. Again, this is an area where sensor fusion can play because you're pulling off both distance and speed. Now you can do a lot of things. If you assist it with angles, you now see that something's turning in the field of view. As costs decrease, radar systems will be installed in more class of vehicles. Right now, the long-distance radars are priced anywhere from $125 to $150 for up to 200 meters of detection. Those medium to short are priced at $50 to $100, and they're actually shorter range, so basically anywhere from 0.2 to 30 meters. And hopefully there will be enhancements there so that we can look forward and backward through assistance and also bring in other sensors to help. These are two, both from Bosch, both the long range, second generation, long range, third generation. So you can see what's taking place on packaging and what's taking place on circuit board technology, going from a all-on-one here and all-on-one there to splitting it out and being able to achieve high performance on this board and all the accessory type of electronics on another board. Again, choice of new materials. The device technology changed from gallium arsenide to SiGe, which is silicon germanium. High bandwidth and performance. Package got integrated differently. And then the processor power and radar on each individual board was better use of the real estate. Long range, I won't go through this again, but size matters, power dissipation, low noise, antenna design, and DSPs make up this whole system and can make it more efficient as time goes on. These are the vision system type companies, and you're very familiar with some of these. These guys are coming on board, and I know full well I was visiting in Belgium on semiconductor, and they have great ideas as well as to how to add more functionality for automotive applications. Here again is a Yole diagram. Originally, not too much usage here from volume in the automotive industry, but there's no reason not to believe that this will shift out, and that's automotive right there, pushing it out further for more volume shipped. But these are the current status of the CMOS image sensors within the marketplace and how it's changing, could change, and will change. These are the types of systems for CMOS imagers. In this case, size matters again because of the mobile, but let's release the constraint of that and put more functionality and maybe put more imagers within the automotive systems, and this tends to trend pretty well, but cost has been beaten out from the mobile industry. And there'll be a lot more need for higher I/O because it won't stop at an image sensor. It'll actually have a processor right next to it, which in some systems don't exist. So the closer you can get a processor to the image sensor, now the data rate can be really fast, much faster than you can think of in a cell phone. Great question though, is why does size matter in imaging? Because we'll take full advantage and we'll want more. Here again is more of a smart camera module. It's got a few technologies. It's got the imager array on top. It has also embedded die, so you can put chips within basically a circuit board material and build it up and then have very little real estate other than the image sensor. Or you can do this in glass and put an additional chip here and get some very high speeds going on between the image sensor and the processor. And again, laser systems now starting to be embedded in lights, headlights. really doing an excellent job. And this is the complexity. It's coming from how it works for the i8.
I follow an i8 into my work every day. It's not me, but I get very jealous because it's such a beautiful car.
And one of those things is the fact that it's got some really nice headlights as well. Packaging, it's an enormously important part of making sure that MEMS and sensors are still manufacturable. Technology and economics are starting to drive both a convergence and consolidation. And prior concepts and processes inhibit us from moving forward for this convergence. And we're starting to see that even these prior concepts are fading away. And this is true for many things, but probably even more so true for MEMS and sensors. Packaging is that the landscape will look completely different in the future than they are today. A lot more innovations taking place. So a little bit of a summary here. ADAS is a driving factor, mainly because of the semiconductor content that's going into vehicles. Higher level of ADAS, more electronics. Redundant systems are very important here. It probably doesn't need to be as great as aircraft industry, such as a 3X, but a 2X is pretty acceptable. Sensor fusion, when you start to combine both LiDAR and radar, you can do some pretty amazing things on front collision avoidance. There's going to be a lot of I/O, input-output, and therefore it will take a lot of sensor fusion to make that work. Probably shift from a little bit more localized to a centralized sensor fusion. Plus, we'll shift from our ball grid array packages to flip chip and fan-out wafer level. Image sensors will start to fuse with processors, and they're desirable mainly because it's localized processing. So you can look at a pedestrian up ahead. You can do faster image processing speeds. That usually drives to having a higher speed process node at the silicon level. And a stacked die is pretty attractive, but again, you have to meet the reliability requirements. It's kind of key that all of these follow, but I think we're going to see a lot more image sensors because of their established base in mobile to go forward. So hopefully I've convinced you that both chips and integration are the sources of automotive innovation. Automotive innovation leads to new technologies, the newest technology. Combining sensing and imaging is probably going to be a more comprehensive solution, so LiDAR and CMOS image cameras. Redundancy is pretty important, particularly for the 360 type fail-safe systems. Each phase of the autonomous vehicle will focus pretty much on the chips or semiconductors and MEMS, the packaging, and the way we integrate them. It'll drive a lot more innovation. And we always have to have this mantra of systems, modules, packages, and devices in order to meet those challenges. We better understand that complete integration chain. And then basically, complete supply chain has to deal with cooperating at these levels to get the best possible solution. So next generation MEMS will pretty much leverage, as I said, new materials, new processes, new technologies, and new materials, or new equipment. Co-design should take place so we don't say he dropped the ball or she dropped the ball. We always deal with design for manufacturability. Let's get it to a Six Sigma quality or better, and then innovation and brainstorming. I put the quote there because I believe it every day, that we just don't have a crystal ball. We definitely can't look forward until we've looked back and tried to make what has been in the past a lot better. We have to trust that what we're doing is right, and it should make all the difference in our lives. So we go from traditional through a set of developments on into newer domains that we're not quite as familiar with. But I think that's the way the future car will slowly evolve. Give credit to all the research for market and technologies. Each one of these I monitor on a daily basis, mainly because it's in my title. little bit of further reading, one on Gordon Moore back in 1965, saying this is the way technology should trend for chips. Another one called Sixth Sense, the driver's Sixth Sense, that's in the IEEE Spectrum, available online. And Dr. Ralph Tamala from Georgia Tech, who was a former IBM expert. How do we get there from here? First of all, I think we have to talk to each other for sure. Communication is a very important part of this because somebody that's developing what seems to be a very unique solution that probably won't apply to automotive, to give them the time to give their elevator talk, a lot of times will convince me that's a pretty unique and direct something that I always work in analogies. If I don't know anything about fluids, I'll liken that to electrical. And I get the analogies pretty quick and the principles. Another thing is, what got us here today will not get us to the future. Not that we forget about it, as that Steve Jobs quote said, but it's important to understand that we've got to throw off the old norms of this is the way it was built in the past. We've got to continue on or not show too much of an upset. I think we need a few upsets in here so that we think, man, this will further enhance. So I don't have any direct, this is what we've got to do, but I'm saying be open to what is innovation. In some areas, it may come from the mobile industry and how they applied a certain chipset to get what they were after. In the other cases, it may be an industrial application. So the more we think we're different, the more we are the same, and we can learn from each other. I think that's about it. So I'll end it with that. Thank you for your attention, and it's been a pleasure talking today. Aaron?